So we've talked so far about how to find your transfer function given h of n, given the difference equation, block diagram, or filter specification. We've talked about the four types of notation, whether it's in z to the positive one or z to the negative one, whether it's factored or not factored. And we've talked about poles and zeros. And we've talked about finding the frequency response given h of z. That's what Charles just did. This second part, though, how to find y of n given h of n, given an input and impulse response. Let's do that right now. So find y of n given x of n and h of n. Will, tell me the first idea that you have to do this. You want to find the output, you're given the input and the impulse response. We've been doing this for a while.
Seems like a pretty simple geometric or algebraic manipulation, since you know h of n is y of n over x of n, or in the z form. So if you go to the z plane and then you do that, it should give you a inverse version of your y z and then transform that back.
Yes, exactly. So the right answer is to say use z transforms.
You tried to trip me up. I caught myself.
And find, I did not try to trick you, and find the product. Well, just to be complete, is this true?
No.
No.
It'd be convolved would be true.
Yes. So there's our second way to do it. And the second way is really the mainstay of DSP. It's what we do. We've got computers, we've got a finite number of input samples, a finite impulse response, and we convolve the two. But last class we learned one more. We learned that we could recast x of n as this complex exponential. Even if x of n is a cosine, or if x of n is a power series, like 1/2 raised to the n, we can still recast it as this complex exponential. We just might get some really weird frequencies that might, be lons and j's and things like that, but we can do it. And if we do that, then we can say that our output is exactly equal to our input, just multiplied by a constant. And that constant, which might be complex, is our transfer function evaluated at that omega naught. So it's a particular number. This isn't a variable anymore. This isn't a transfer function. This has been evaluated at the omega naught of our input. And when we do that, we find the output steady state portion, because what we're doing is we're assuming that if the input can be represented like this, we're saying that the input is in steady state. And then in general, if it's not truly steady state, we can say that the output is composed of two parts, a steady state one that we've solved exactly above, and a transient one that will decay. And maybe we can just ignore that transient part that decays if it's not important to have an exact solution. Or even if it's important to have an exact solution, if our system is FIR, we know our transient decays down to 0 for n greater than or equal to the m of our system. Okay, questions about all that? This last interpretation has a big meaning for what we're going to cover next, which is, man, that was anticlimactic. There we go. Which is our geometric interpretation of what a transfer function is. A big thing is you're given this and you want to quickly see, hey, is that a low pass filter, high pass filter, band pass filter? What is it doing? In order to do that, we need to find out the magnitude of our transfer, because if you start thinking about this in terms of the last thing we just talked about, if you plug in a cosine, let me go back to where we were. I don't want to spend the entire time doing a complete review of last class. What we said was that if you plug in, say, a cosine of omega naught n into our system, what we get out is the exact same as what we put into it, just with some sort of phase shift and some sort of amplitude shift. And we don't need to use z transforms to figure out what that amplitude and phase is. All we need to do is evaluate our system transfer function at e to the j omega naught, where that omega naught here is the same as that omega naught here, is the same as that omega naught here, and voila, out pops a magnitude at an angle that solves our equation. So it would be very useful then to be able to directly read out what kinds of input frequencies this system transfer passes and the system transfer function stops, because that would tell us what kind of system we're looking at.